building cost of a heap. Yeah. So in this part, we want to look at how much cost do we need to construct a heap from any given array. So when we have an array of numbers, before we sort it, we want to build a heap. Yeah. So if the building cost is too high, then we should not use this method. Yeah, because that cost should be considered in the overall cost. Yeah. So this part, we want to see how high is it, the total building cost. Yeah. So let's look at the details. Combine the cost of all heights. So what's that? So first we need to recall the building procedure in our part A. In our part A, I gave you one simple example. So given the array, how do we build a heap? First, we arrange the numbers, just following the given order in a binary, near complete binary tree, right? So after that, we need to apply the max heapify operation bottom up from the, lower level height 1 nodes. Yeah. So look at height 1 nodes. Yeah. Moving up. Okay. So fix it. Each level we try to fix all the nodes in that level. Okay. So then going up, finally when we reach the root, then we complete the heap building procedure. Yeah. So based on that, now let's look at how much cost do we need. Yeah. Cost of max heapify for all nodes of height h. Yeah. From the last video, B.1, we get that information. We get the number of nodes with height h. So we use that number, that expression. Yeah. So that expression, remember, so we have that precise expression, but for this particular situation, remember that expression less than or equal to this expression, because this expression is easier to estimate the whole cost. So we want to select this, use this expression, less than or equal this one. All right, so this is the upper bound for the number of nodes with height h, okay, height h. Yeah. All right, then for each node, how do we fix it using the max heapify? So remember, if we recall, suppose there is a node here, okay? Then we need to fix it level by level until we reach the bottom, right? So how many steps do you go? Height h. Here you can see, here we need to use that height h. Yeah, because you're going down until you reach the bottom, right? Yeah. So the operation, the cost you need, big O of h. For each node, but we have this many, so the total node for that whole level, multiply these two, so you get that expression. Okay. All right. Next, we need to consider all different heights, right? Yeah. More specifically, heights from 1 to highest possible 1, floor function of log base 2 of n. Yeah. Remember, the leaf level 0 height, we do not do any max heapify. Yeah. So here we skip the leaves. No max heapify operation on all leaf nodes. Okay? Yeah. Nothing to fix, right? Nothing to fix. Yeah. So for that consideration, we can write the total build cost in this summation. The level from 1 through the top level, each level, the cost is this much, the product of these two numbers. Next, we need to estimate this expression. How much is this expression? All right, so let's do some simplification. First, we want to remove the ceiling function, because ceiling function is not very convenient for processing. So we want to get rid of it, ceiling function. So we use n over 2 to the h plus 1 plus 1. Because if we add just a 1 to it, we will get a number greater or equal to the ceiling function. So we get rid of the ceiling function, this expression. But this expression, we can split into two summations. The first one, multiply big O of h, we get a first summation. That 1 multiply big O of h, we get a second summation. But the second summation is much easier to estimate because it is much smaller than the first summation. So we want to see how big it is. All right, so big O h, Here you can see, adding integers from 1 through that number. We apply the formula. The formula is approximate this much. So we can write log of n squared. Log of n squared. So that's the cost for the second summation. Next, the harder part, the first summation. So for the first summation, we expect much greater than this one. Much greater than this one. So the first one will be the main term. Second one, the minor one. We can even ignore it. So our focus is on the first summation. All right, so now we estimate the main term. This summation. So for this summation, you can see that n, we can take that n out. Because that's the common factor of all the terms, right? All the terms. So we can take that n out. So we only need to consider that summation part. So, and to estimate that summation, we can change the upper summation limit to infinity. In that way, we do not need to worry about what is the upper limit. So we can even consider more terms. We can go to the infinity and see how much is the summation. So next, we need to calculate this summation, new expression, that summation. So the next slide, we will find that summation number. All right, calculate the summation. So for this summation, so you can see it is not a arithmetic series, it is not a geometric series, but actually we mix them. So if you only look at the numerator part, do not look at the denominator part, only look at numerator part, it is an arithmetic theory, a series. But if you look at the denominator part, it is a geometric series. So you mix these two, now you get a new series. All right, so let's do the calculation. When we do it, we need to use some very smart trick here. So look at this technology. Simple technology, but it works quite well. Yeah. So we do this. Look at the denominator. Power of 2. All power of 2. Different powers of 2. Okay? Yeah. In ascending order. 1, 2, 3, 4. Yeah. 2, 3 going up. Yeah. So you can see if we multiply 2 both sides, 2s equals, now you can see the denominator still power of 2, yeah, but shift a little bit. 2 to the first, 2 to the second, and so on. Okay, yeah. So if you look at that, now you compare these two series, term by term, you can find something very interesting. Yeah. Compare these two terms. They have the same denominator. The numerator difference is 1. Denominator is the same. Okay? Look at the next two, same property, same denominator, the numerator difference also 1. Yeah. And so on. All the way down to the end, yeah, you know, no end, yeah, yeah. You can find the same property. So we can take advantage of this property. Yeah. So we call it, you know, we combine the like terms. Yeah. They are like terms in pairs. Okay. All right. So we do this operation using the second series minus the first series. Yeah. So we get S. Left-hand side S. The right-hand side, the remaining part. Okay. First term, no pair for it. We just leave there. Okay. The second term, difference from the first circle. Okay. Then each circle, one term left. Okay. Yeah. And so on. So you can see after subtraction, you get a geometric series. This infinite geometric series, you can find the summation easily because we can apply the formula. So remember, what is the formula? Okay. Infinite geometric series, the formula, very simple. Yeah. The first term, 1/2, over 1 minus the common ratio. So what is the common ratio? Term by term, also 1/2. Okay. So 1/2 over 1/2 equals 1. Yeah. So the answer is 1. That means the S is 1. Okay? Yeah. So you can see the original series looks pretty complicated, but after we do some basic calculation, we get the answer equals 1. Okay? So nice. Okay? Yeah. Now we can get our conclusion. After that, we can get our conclusion. What is the building cost? If we build a heap, how much is the cost? The main term, the first summation, the main term, because after we factor that n out, remaining part, just the 1. Okay, 1 times n, so the building cost, big O of n. That's simple. Big O of n. Yeah. Okay. Now you can see if we want to sort the array, usually we expect the total sorting cost, big O of n log n, right? Big O of n log n. Now to build a heap, we need to pay this much cost. Yeah. It looks acceptable. Yeah. Because smaller than that, it looks acceptable. Okay. Yeah. So with this analysis, so we feel it's okay. So we use if we use the heap data structure to manage dynamic data and maintain the elements in some order, it is fine. Yeah, the cost is under control. Okay. All right. The second term, you can see compare this one with the main summation, the second summation, much smaller. Yeah. So we can comfortably ignore the second term. So at the end, we use the big O of M for the total building cost of a heap. Yeah. All right. So we complete B.2. Yeah. Next, the last video of this part, B.3, we will do the heap sort and some efficiency analysis. Yeah. All right, so let's stop here. Yeah.